So from now till a while, till we end operation transformation, we are basically going to discuss consistency in various forms. Okay, and we looked at consistency problems that can occur when people have concurrent operations, and now it works out. Okay. So when you implement causality, you have to do some work now. Okay, it doesn't seem very complicated, and it isn't, as long as you understand the theory well. Okay, but you have to implement vector timestamps. You have to implement the buffer. You have to change message sends and receives. To do that, to timestamp and untimestamp a message. So let's talk of software engineering issues now. Okay, so I've got my model, and I've got some receiver somewhere also. I could change my model to send the messages, and whatever my receiver is, I could go and change that to remove the timestamps to buffer things. Okay, so let's consider the model and the receiver to be the model, the semantics right now. Should we direct? So I'm putting this question: should we change the model directly, and should we change the receiving filter, the receiving receive listener directly? And the answer must be no. So what's wrong with doing it in the model? Practically, what bad things can happen? And if not in the model, where should we put this?
It would be nice for it to be in the messaging system for you.
Okay, it would be nice if it's in the messaging system for you, the system I gave you guys.
Yeah.
So what would your assignment be in that case? Well, so from an assignment, firstly, why shouldn't the model have it? It would be nice if it's in the messaging system to reduce your work. Okay, let's assume that's not the issue. It'll be nice if it's if it's not in the communication system to increase your work, right? But those are not good reasons. So why should it not be in the communication system, and why should it not be in the model? And if it's not going to be in these two cases, in these two entities, where else should it be? So let's try to find a logical reason why it should not be in the model.
Like guaranteeing that consistency should not be a concern of the model.
Is the consistency we saw, is it any way application specific, model specific? It didn't even look at the contents of the messages, right? It's a separation of concerns. That means if I change my model, I should be able to use the same consistency mechanism, right? In fact, is it even dependent on model-based sharing? Could it be used in window-based sharing? Just like your locks. It's just looking at messages. You could be ordering telepointer messages, as we talked about. Okay? So now, I want to increase your work, so I don't put it in the communication system. Why should it not be in the communication system? Is it tied to how the communication is going? Is it tied to whether it's, RPC or message passing? Yeah.
Well, it kind of seems like a layer built over top of the communication system, like that encapsulates it.
Yeah. So we designed an algorithm. We defined an algorithm as an extension of two-way messaging. Why shouldn't the implementation also be an extension of two-way or n-way non-ordered messaging? Okay. The two-way case we ordered as we layered as something on top of reliable messaging, and why not do the n case also on top of just ordered on reliable messages? Okay, so model has to do the extra steps mentioned in the previous slide. Model may not want overhead. Okay, and the other thing is, at some point you might want the overhead of causality. At some other point you may not want. Okay, in some cases you may not care. Okay, in IM tools people don't care of causality. Okay, so why pay the overhead if you don't want it? And if they are kept separate, then you can just go and decouple, not even use one component. Okay. And in fact, in IM case, people don't care about it. If the communication was being relayed, causality is automatically ensured. Okay. So you want to be able to dynamically remove the causality code in these cases. Okay. And may want causality in replicated window systems or some other model. So put causal semantics in infrastructure. That's the next question. And like Nick said, they're just independent of the communication infrastructure and application. So there's separation of concerns, and application code is unaware of causality code. Communication infrastructure is unaware of causality, and can add, remove, change causality implementation. So what kind of pattern can we use? So what kind of, is there some general pattern we could use to add and remove causality? Something you guys might have seen before, actually. It's not the vetoed model. Okay, nothing's being vetoed. Is it observer? What are we really doing? I mean, when a message, so there is the application, there is the communication infrastructure. And what are we really doing with causality? At the sending end, what are we really doing? So the application wants to just send a message, key pressed, right? Communication infrastructure will take any message and send it. And what is the causality code doing to the message, key pressed?
So this is like an event queue.
This is like an event queue that you're intercepting messages.
Mm-hmm. And reordering them, potentially throwing them out.
Throwing them down.
Modifying them.
Okay, at both ends, right? So you are intercepting messages that go out, and you're intercepting messages between the communication infrastructure and the application, and you may be reordering them. Okay, we left here last time. We came up with an algorithm for causality, and we generalized the two-user case to the n-user case. And again, I used networking analogy to come up with the algorithm. And that algorithm, the way I present it, is not the way you'll see in other papers. And one of the reasons is that the other papers are addressing fault tolerance, and they're combining that algorithm with fault tolerance, whereas I'm just addressing group communication that arises in collaborative computing, assuming there are no faults. Okay. Actually, that's one area that hasn't gotten much attention in CSCW, fault tolerance. And you can say that's okay. CSCW already does replication for availability, so fault tolerance just comes from it. Okay, so we wrote a little paper on that issue, but there's been no formal definite look at, what if there are 2 faults and versus 5 faults, and how many computers do you need to be able, what happens if there's some malicious computers. So there's a whole literature area there that hasn't been looked at by CSCW, and it's not clear whether the issues that arise here are different from normal distributed computing. Okay, so we looked at this algorithm, and the question was how to implement it, and we wanted separation of concerns. So we said, okay, there's some collaboration, causality unaware application that somebody's written. It could be a shared window system, it could be a shared model system, it could be sharing one model or another model. And then we can design some kind of communication system, group communication system, and group messages is one such system. There could be other systems too. Okay? And we don't want to tie, I told you already there are many causality algorithms depending on what the context is. And even here, depending on how you handle concurrent messages, there can be many algorithms. So let's not burn anything into the system. In any case, if I burnt it into the system, there's no assignment to give you guys. So we wanted something that was going to be independent of both of these systems. And we just, I think Nick pointed out the analogy between this and our window systems. And just as in event queue, you intercept the messages, we are going to intercept messages that are passing between these 2 agents and provide a causality-aware proxy. Okay, that was the basic idea. So just as you put a proxy between an application and the window system, you put now a proxy between a causality-unaware application and a causality-unaware communication system. Okay. And the whole idea is that this particular proxy is optional. You may or may not have it. Okay, this is just like web proxies again, just a proxy pattern. And so the communication system, for this to work, the communication system must allow interception and interjection of messages, okay, just as we saw in the case of the shared window system. Okay. So how do we do that? Well, we're going to have, there's two different entities involved here. There's two different parts involved here. So we'll create a send filter and a receive filter. Okay. And so in general, there is a whole pipeline of stages in the system. Okay, so this picture is not quite the one that is that you want, but it's a simplified version of what you have, which I'll show you pretty soon. But the whole idea is that there's a pipeline in the communication system, and at some stage in the pipeline, you can put a send filter and a receive filter. Okay, so it's not quite like this. The messages bounce back from the system, and which we'll see in the next slide. The default filter simply forwards message to the next stage, okay, in that pipeline. And we need a way to replace the default filter with custom filters. Okay, so this is all software engineering principles now, no algorithmic principles. But when I'll finally end up with a new algorithm that takes into account this architecture. And before I go to the exact picture, that was the approximate picture, let's look at all of our assignments and see whether filters would be useful in other assignments also or not. Okay. So in this assignment, there's no communication. In this assignment, you were basically passing messages and doing what's called best effort. You're just passing messages and hoping for the best. Okay? You were not delaying messages, you were not doing anything stupid, but you're not doing anything smart either. Okay? That you could provably show was smart. Okay? Here you were sending model messages, here you were sending window system messages. You're not doing this assignment, but you might remember this, that when there was jitter, we were making a jitter, a whole trail. Any filtering going on here?
So when we're moving around the telepointer, we don't want to send every single event.
Immediately.
So, yeah, so a filter could do that.
So it could send. In fact, you guys could have done your extra credit using a filter too. Okay, I didn't get to filters at that point. Otherwise, I would have, suggested that. But in this case, you are buffering everything. You are going to display everything, but you're buffering them so that you could create a trail. That's a form of filtering. Okay, only the receiver does it. The sender doesn't do it. Right? Causality, reordering. Okay, and the sender now must go and timestamp the message. Okay, so the sender has to do some work, the receiver has to do buffering and reordering. Okay, and operation transformation, you haven't done that, but you saw the demo. Can you imagine, can you see what kind of filtering might be going on there? What does the word of operation transformation suggest? Transformation. Okay, so this filters you're going to use both in this assignment and the one afterwards. Okay, and you could have used it in your previous assignment when you were in that sending stage, you were filtering out certain messages. Okay, and the other cases were unfiltered. Okay, so this is general. And now let me show you exactly how. Good. You filtered on what?
Behind the law, veto, that is kind of filter. They're not sending those.
Yeah. So filtering is something that I'm suggesting could be put orthogonally to everything else. Whereas your lock semantics was pretty closely tied to that. Your locking guy said, let me just send something stupid. Okay. Whereas in the other cases I'm saying you might want the application with trails, you may not want trails. Right? Why should the message path go through the trails code if you don't want trails? And all the bugs in it and all the security issues in it take place if you don't require it. Okay? Similarly with operation transformation, you may want transformation, you may not want transformation. Or there's a zillion operation transformation algorithms. And there are zillion algorithms mainly because it's very hard to prove those correct. So people just say, okay, I found a bug in the previous algorithm. I fixed that bug. And here's they don't call it bug. They call it puzzles. That there's a puzzle why this other person didn't fix the problem. So let me solve that puzzle. And that's another story. Okay. So here's what happens. The sender sends. So this is how it works in your system. You say two others to the communicator. Okay. The communicator does some processing. The message goes through certain stages. At some point, it says, "Hey, application, do you want to filter this message that I'm about to send, or that I will send later?" So it says, "Okay, if you have a filter, it'll always go through a filter, and if you don't have your own filter, it'll go through just a forwarding filter. Because there's only one filter in this system. You could imagine a pipeline of filters, but I designed another system with that, and it becomes very complex. So in this system, I say, if you want a pipeline, you just replace your filter with multiple filters. Okay." And so it filters the message and then goes and sends it to some component that it knows about. Okay, and it says, okay, send message processor, you forward the message through the remaining filters. Okay, and the message goes. Similarly, when a message arrives, you expect some receiving listener to get the message, but we don't really deliver the message directly to receiver. It goes to the communicator. The communicator does some processing with it, creates some message type, sends it to the received message filter, which goes and filters it, and then sends it to the received message processor, which does some more things. Who knows what they are? One of the things it does is look at all the listeners and send the message to all of those listeners. Okay, and it keeps track of all the listeners. That's what really happens. And it goes and calls object received. Okay? And if this was just a forwarder, you would just simply get the message that was received. Yeah, otherwise, what you can do is you may not call object process message, so delay the message. You may call process message on a previously buffered message. Okay, so you have all these options. Okay, so that's really the picture here. Okay, questions? So what's the filter interface going to be now? This picture pretty much tells you. What are the methods in the filter interface that you would need? Process message is implemented by this guy. Somehow it has to know about this guy, which must mean that it must have a method that sets the message processor. Okay? And then filter message is the method it defines. Okay? Filter message, process message. Okay. So set message processor, and we define one interface for both any kind of message. Okay, so we are making it totally independent of what the exact message is. We know that the message we receive is the message we send out. Okay, so both message processor and message filter are parameterized by the type of the message. Okay, so received message or sent message. It'll in your system it'll be either a received message type defined by communicator or a sent message type defined by the communicator. Okay, and this is called by the communication system when new message to be filtered is available, and this method is called by the communication system to set the message processor, saying, hey, this is your next. Okay, so if you know Unix pipes, they have a standard input and standard output. Okay, and these standard input and standard output can be set by whoever created you. Okay, and that's how your program is not bound to a particular file or to the console or to another processor's pipe. Okay, similar stuff is happening. Yeah, in fact, this was totally inspired by pipes. I grew up with command line programming, so pipes were wonderful, and you guys who use the command line, or I'm sure also find them useful. Okay, so call by communication system when pipeline is set. A message processor interface, pretty much is derived from that. It's just got a process message. Okay, and this is called by message filter to process message. I'm giving you all these details because this is an API. which you need to use, for which there is no external documentation. Okay, so this is the documentation. And then, so when this is a sent message processor, then succeeding state, this stage, the message is broadcast. When this is a received message processor, it just delivers the message to all the listeners. Okay, so we've got this architecture. And in the unfiltered case, what happens? I told you already. We've got this message forwarder filter that basically whatever message it receives, it just forwards directly. Okay? And whenever the set message processor is called, it just stores that processor in a variable so that it can forward the message. Okay? You'll have to do something similar. You'll have to do these kind of things plus more. Okay? So this is just some code to show you how this stuff can be used. Okay? So this is instantiated as both a send and receive filter. Okay? They're both just basically forwarding. So you'll replace the custom receive and send filters. That's my sent message filter or my received message filter. Okay. So when you write your own filters, you're going to do different things based on the messages, and you need to look into the message. Okay, because you just received a message and you have to go and find out what the actual, this is the message. You send some object, that's some arbitrary object. That object gets wrapped in some data type that the communicator creates. Okay? And and what you'll have to do is extract that message, the message you sent, from that wrapping message. So you need to know some details about what you get. Okay? And by the way, this wrapping idea, so there's this pipeline idea that comes from Unix pipes. The wrapping idea comes from some other field that some of you guys might have seen, a very popular field today. That you take a message, you wrap it in a bigger message, you wrap it in a bigger message. Networking. Okay? So you send a message that gets wrapped in a message that has got the IP address in it now. Okay? So that's the same kind of wrapping that happens here. So we need to know really what these messages are. And the message that is sent is a send message type. And it's got, it's a subtype of group message. And you can figure out what application it was that is involved in sending the message. And what do you think this is user message and get user messages? Firstly, why is the communication system wrapping your message in a bigger object? Why does it not just send the object directly? You guys remember you've done enough coding, 3 assignments. Is what you get what you sent? What you send is some object. What you get is that object plus the username. So it's got to at least, put that information in. Who sent the message, right? Plus it puts a timestamp and it puts other information too. Okay? Real time, real clock time. Okay? And is user message? So these are messages going between the two processes. Some messages go because of your calls. Some messages go because to make sure that all the audience are in sync. Okay, so if there's a session manager, the local library has to know when somebody joins, when somebody leaves. Okay, it has to keep the state consistent. So you are going to check whether the message is a user message. If it's not a user message, you don't have to do anything. Okay, you have a delayer sort of filter-like object, which will delay all the messages, including the other messages to sort of fake delays. Okay, but in your case, you don't have to worry about the other messages. So you go and say, is this a user message? If so, let me get the user message, in which case I get back the object that was really sent. Okay, and now I can timestamp it and send it now. So what you'll do is you'll timestamp it and then make it, there's also not only a get user message, I should have mentioned this, there's also a set user message. So the message you have, you can get the user message from it, and then you can set the user message to be a different message from what the application sent. Okay, so the application sent a particular message, you can timestamp that message and then set that to be the user message. Okay, so if I don't remember there's a set user message also. Okay, I'm trying to provide you only with the methods that are relevant to you, and that is another relevant method call. Okay. So send message filter must implement message filter send message. If it's user message, then get user message is the object sent by remote site. User object will be replaced with timestamp object by filter by calling set user message. Okay. System messages such as client joins and leave status update message. System messages are messages such as the client joins and leave status updates. Okay. And receive message extend the same group message. Okay, so you have all that information that you had there. Plus, you can get the client name, the name of the client that sent the message. Okay, which it would be useful for sure in your OT assignment, and here too, because you need to know which timestamp, which count to increment. Okay, so you're getting closer to your implementation goals. Okay, so it must implement the message filter received message. Again, I'm giving you some details so that your assignment is done more easily. Group messages unite send message and receive message, and we know again that if it's a user message, then get user message is the object, and user object will be actual user object extracted from timestamp message. Okay, so what you will do is you will get a timestamp message object sent by this that the sent filter put, and what you'll have to do is get the object out of this timestamp object and deliver it to the application. Okay, so this, like I said, I'm making things easy for you. Okay, again, I think from what I've heard from you, despite all the details I give you, there's enough challenge. Okay, so I'm happy about that. Let me know if there's not enough challenge. I can always remove some of these details. Okay, you won't find many courses that do this, and when I've taught stuff like this before, I haven't given these many details, and I know students have had trouble, and I think I mentioned this before, but my favorite courses when I was a grad student were the compiler courses. And if you look at any compiler book, they'll give you pretty much the full algorithm. Okay? And yet, implementing a compiler, is something people, find very difficult. So I figured that I can give you more assignments if I give you more details, and the learning will be a lot still. Okay? So. Okay, so this is a picture I showed you. Do you need any state to be shared between the send filter and the receive filter? What state? Yeah. The vector. Okay. What is the send message guy doing? He's attaching vector timestamp and changing the vector timestamp. What is the receive guy doing? He's comparing the vector's timestamp with the timestamp in the message, and also changing the vector timestamp. Okay. So this makes things a little bit more complicated. We have two pipelines that need to coordinate with each other. Okay. So we need so this is the pattern I would suggest you do. Implement that. Bulk of the code is done in this causality manager. Okay, think of this as a combined receive and send filter. Okay, I didn't keep one filter for both because in certain applications you just need send filters, in certain applications you just need receive filters. So I made them independent, but the flip side now is that you've got to make them dependent now. So let both of them refer to some causality manager, which is like a combined filter, and the bulk of the work will be done here. Okay? And it'll keep the received, the timestamp. Okay. So bulk of work done by shared causality manager. So I've shown you the dynamic steps. Okay, that you have to timestamp messages, you have to untimestamp messages. Do we have to do some steps before communication starts?
We need to instantiate and set up the filters and the causality manager.
We have to set up these agents. Okay, and anything else? I mean, these agents, but in terms of that's in terms of this architecture. In terms of the algorithm, is there some algorithmic step that has to happen? Initialize the vector. With how many entries? Okay. So what are we going to do? The joins happen dynamically. What does causality mean when people join dynamically? What does broadcast and causality mean? Yeah.
So, is every user guaranteed to see the other users join in the same order? Because if we're going to have these vectors, we need to be able to associate each element of the vector with a user, and there needs to be a consensus between all users about what their element is, what their ID is.
Okay, that's very good. If you're sending a vector timestamp, okay, and if it's really this kind of timestamp where there's a position, so this is even a more fundamental question. How do we all agree on an order? In your system, what could you do?
Just instantiate always in that order.
But so one thing is that everybody receives joins in the same order, but you know, what does that mean? A and B both joined. Sure, C got to see A and B in the same order, but in what order do A and B put themselves? Each site has a name, right? We assume it's a unique name. So what could you do? I mean, I think you answered your question. Alphabetical order. Or you could just be in more space. This is how I implement it. I just send a hash table. Okay. So I send a key value pair. And this allows for people to join dynamically. Okay, but then it fails in other ways too. This allows, at least, in principle, or it allows extension to that. So we've solved the problem of having the vector timestamp, be consistently interpreted at all sites. How about, what happens now? What constraints do we have to put to make this work about joins and message communication? In causality, when we have causal system. In a causal system, you cannot get a message unless you received all of its causes. So what if A and B join? They send a message to each other, and then C joins. What happened to the message that was sent between A and B? It either is sent to C or is not sent to C. If it is sent to C, that means we have to buffer the messages. Okay, and this is something that I didn't get into and I don't quite implement in the system. That's called latecomer messages, that you have to basically buffer the messages somewhere. You have to assume some kind of relayer or some agent or some particular process has all the messages. And when a process joins, it gets all the previous messages. And this becomes real fun because while it's getting messages, new messages are also being generated. And you need some kind of synchronization protocol. Okay? So I didn't implement this myself. And I didn't, ask you guys to implement it.
So is it just like basically a history data structure that
Yeah.
just keeps on?
Yeah, but that history is changing unless we go and freeze the state and say whenever a user joins, okay, let's go and freeze the state. Let's have some kind of consensus that it's all frozen. Now the user joins. And actually, this is what I did. One of my PhD students did an implementation like this. And he allow the messages to go back and forth. And then he had just this one synchronization step that he did in the end. And you know, at least we convinced ourselves it worked. Okay, and we convinced the referees that it worked. Okay, if we don't send C the previous message, then it can't receive any message because it hasn't received the messages that caused the new messages. So what we'll assume in your assignment and this algorithm is that everybody joins and then they don't change. Okay, so there's a set of people, they join, new replicas aren't created while messages are in transit. Okay, so there are two phases. There's a static phase when this particular timestamp is created, then a dynamic phase when it's changed. Okay, so that's what we'll assume. For extra credit, if you want to do other things, that's great. Okay. By the way, just because I haven't mentioned something as an extra credit doesn't mean it's not extra credit. As many of you guys have seen, I give you points for something that I thought was useful, even if I didn't ask for it. Okay. In fact, I'm happier giving points for that because you get extra credit for thinking of a new feature and implementing it, rather than just implementing something I thought about. Okay. So feel free to do more than that. Okay. So to create the initial timestamp, so as this picture indicates, the timestamp is created by the causality manager, right? That's where it's stored. And for you to create the timestamp, it must be able to intercept the client join calls and the client leave calls. Okay. So not only is causality manager talking to the two filters, but it's also talking to the causality unaware system. We assume that unaware system provides a method to intercept joins and leaves. In fact, it does. You guys have seen it before. I'll just remind you what it looks like. So you have to use this particular feature also to implement causality. Okay, and I say client joined also mean client left. Client left you don't have to worry about because you're assuming a static picture. Okay, but that is something you could do if you're doing some kind of extra credit. Okay, so when to add component to vector? When the client joins. Listening to client joins, you just go and say communicator add session message listener, and you're going to add causality manager as the listener, which must then implement this interface, which includes client join and client left. And there are, this is something I went through earlier. I don't have to go through again, but this is just so this is a reminder. Okay. Questions? Assume the first message is sent after all members of the session have joined and no message sent after the first user leaves. Okay. If you're going to allow dynamic session changes, then you have to support latecomer messages. Okay. And ideally, latecomer messages should be provided by the communication library. And I don't provide that, and I don't provide it for two reasons. First, I don't want to implement it, but actually I have implemented it in many other cases. But I might in the future give some assignment that requires you to extend the system with latecomer messages. So the less I put in, the more I can ask the students to do. Okay, so this is what the communication system looks like in your last 4 assignments. Okay, and you have to change this picture to this picture. Okay, so the question is, what kind of API is provided to install your own filters? And the obvious thing to do is to have, let's say, okay, you are aware of communicator. Let the communicator be aware of filters. And you just go and say, communicator set filter to this. Communicator set receive filter, set send filter. Okay? That's not what you'll do here. I'm going to make you do things in a much more roundabout way because I want you to learn an important software engineering concept. What might be a problem with this? The communicator is not one monolithic program. The communicator is just your entry to this whole system. There's many components there. So we might not want the communicator to know about the fact that filters exist. Okay, why separation of concerns? In fact, you may want to switch many components in the system, okay, and put your own components. You want an extendable system. If you have an extendable system, you want to allow components to be switched. And ideally, you don't want any one component to know about all the other components. That means anytime you add a new component to the system, you have to go to this library and put a set filter and a get filter. So, assuming this is what you want, is there some concept some of you guys might have seen before, or you can invent, think of? A very famous pattern. Patrick is not here. I suspect that he would have immediately come up with that pattern. Or maybe not. Sometimes the answer is in front of you and you don't quite see it. So this must be a pattern that has to do with instantiating objects. And you guys might or might not have seen that pattern. Anybody done a software engineering class? Design patterns class? No? Factory. Good. You're all ready for your PRP, you know? So could the factory be used here? We had message forwarders, and we want to replace them with send our own filters. We want to instantiate these objects. If you're going to use, and what is a factory?
I just know the name, actually.
You know more than the name. How did you guess factory and not something else?
You said instantiate new file.
Okay, so so
Well, that's a clue.
that's a clue. And the word factory to you indicates that it instantiates, right? Anybody want to define a factory? You can instantiate a class by saying new class.
A factory is a class or method that wraps a private constructor and controls how an object can be, how an instance of a class can be instantiated.
So you're saying a factory is some method in a class. Because
Method or a class.
class can't instantiate. Some method has to instantiate, right? A class can't do any work. Class does its work through methods, right? So it's a class that has a method that is used to instantiate an object of another class, right? Which could have a private constructor that's visible to this class but not to the other people, so that you don't use the private constructor directly, you as a client, which is other than factory, okay? So that's a more specific definition than what I'd like to use. I'm not going to disallow that class to be instantiated directly by a program. It's probably a good idea to do so. But I'm going to just say that a factory is an object that instantiates another object. Okay? And is that something you, on your own, came up with, the private constructor, or is that something you've seen somewhere?
Something I've seen.
You've seen?
Was classes having a static factory methods and private constructors
Okay.
was the most common use case implementation I've seen.
Okay. So, and you know, that's certainly safe. Okay? But if you want objects to be instantiated only through factories, then that's good. But in this case, you could define something that could be, in some context, be used directly, and in other contexts be used through a factory. So I'm going to be a little bit more general. There is this book that is, you know, the Bible of design patterns, and I wonder if how they define it. Okay? And maybe they define it exactly like this way. I use these patterns like you. I look at the English word, and how these design patterns came around was that people were using them anyway, and the book said, let's just go and document what was happening. So, you know, this book was written while I was already doing things. In fact, you know, I might have mentioned this to you before. The guy called Ralph Johnson at Illinois, and I was at Purdue at that time. So we were in fact friends, still friends. And before the book came around, we used to talk about some of these things. So I haven't really read his book. I know the word factory. I kind of know what it would mean. So I'm using my own definition here, and maybe the correct definition according to the book is indeed a private constructor. But I can see uses for factories even when the constructors are public, okay? Because in some context, instantiating the class may be fine. In some other context, the class may be replaceable by another class. So it's a little bit more gentle, okay? But less safe. So can you see now why factories could be used here? How factories could be used here? By the way, these classes provide static methods or dynamic methods?
Okay,
Instance.
Classes that have static methods that instantiate instances of that class.
So these factory classes, you're saying, have static methods. That's what you've seen, at least in the implementation.
Yes.
Okay. So I would say that they can be static or instance methods. Okay, a factory could be a class or it could be an instance. Okay, and I'm pretty sure that's how Ralph and gang would have defined it also in the book. Okay, though in practice people might have used it with static methods. Okay. So can we see now how this might be used? Just switch. So factories are going to be used to create our filters, right? That's what we want to switch. Okay, so the hint is that, I mean, it's in that context. So how would you switch the objects? So what does a factory do? Factory instantiates classes, right? So you're saying you go in, and according to Nick's definition, you as a programmer can't even instantiate that class. So how can you instantiate the object to that factory? But you're right. Somehow the system is going through a factory to instantiate objects that provides a level of indirection. That's the key here. Okay? And we're going to just go and use that indirection to switch objects. But if I just have factories, and a factory could create a new object each time. It could create a new instance each time, or it could just return the same instance, depending on whether that class is singleton or not singleton. So how could I assign, as an application programmer, how could I assign an object to the factory? The factory is the one that creates the object.
I assign the factory, and factory does it for me.
Okay, so say that again. You assign the factory to what?
To the communicator somehow.
Okay, so so what you have to do is create multiple factories, one for each kind of filter, and somehow tell the communicator, somehow tell the system about the factory. If I told the communicator about the factory, I run into the same problem, because the communicator must know about everything. Okay, so I will go and tell that information to some specific component that's tied to this object. And anybody else seen factories beyond Nick? I mean, studied? Have you seen abstract factories? What might an abstract factory be?
It's like you have an interface, and for different implementations, you can create different factory to initialize those different classes.
Okay, so the whole idea of factories relies on interfaces. Okay, the very fact that you're going to substitute one object with another object, which means you're going to replace an object of one class with an object of another class, means that both classes must implement something common, which is what we call an interface. So factories rely, when you asked me in the beginning of class, do you want me to implement interfaces? Because in 401, I insisted on interfaces. That was the reason, okay? Because you can substitute things. So factories are, in fact, I feel bad that I didn't get into factories in the 401 class, because that would have been a great motivator for interfaces. So factories rely on common interface. And now the factories must also have a common interface so that we can substitute one factory with another subfactory. Okay? And we won't go and tell the communicator about the exact factory. We will go and tell some abstract factory about that. Okay? I used to call that factory selector, and till somebody in my class said, that's abstract factory from the book. Again, you know, I've got the book, I've read it many for certain reasons, but I haven't actually gone and verified. But based on what the student said, I assume that the name implies that it is an abstract factory. Okay? So that's what we're going to do. Again, a lot of hand waving, a lot of pointer waving, but these are all, you know, you can Google for these concepts and you'll learn them. Okay? That's a very common pattern. So filter created using factory. A factory is going to have an interface because we're going to substitute, because we're going to have abstract factories, we will not use static methods, we will use instance methods because these factories will implement the same interface, and so we have to use instance methods, right? At least in Java. How to share objects between filters? Okay, so if these objects are going to be created by factories, how are they going to share? How are they going to share a common data structure? If you were to create the receive filter and the send filter, you would create the causality manager first, then you would go and instantiate, you would use a particular constructor of receive factory, pass to it the causality manager, again instantiate the send filter through a constructor that takes the causality manager, and you've got them bound. Now these guys are being instantiated by factories. So how do you go and have these two objects share a common state? These two filters share a common state? Factories will go and create these objects, so pass causality manager to the factory. Okay? Factories are objects you can create. And you can create two factories that have the same causality manager passed to it, and then this factory object will create a new object to which it passes. Okay, so, sorry?
I guess I'm still not fully understanding what
Okay,
the factory is.
Okay, we'll see an example. But factory is an object that creates another object. Okay? And if it's the one that's creating the object, it's the one that's calling the constructor of the object. If the constructor takes some shared object as a parameter, the factory must itself get that. That's okay. So this is, I'm going to show you exactly the factories used for the forwarder, and then you can go later to the. Okay, and again, if you don't quite understand it, Google. This is something you can Google. Okay? Not the exact interface I provide, but the general concept. Okay, filter created using factory. Shared object can be passed to factories created by program. Okay, that's what we just talked about. How to switch factories? We have an abstract factory, not the communicator. It's an abstract factory that just knows about this concrete factories. Okay, and to that abstract factory, we will assign the abstract, the concrete factories. Okay, if you understand this, I'll just show you code that'll codify. I won't show you how to pass a common object. Okay, that stuff, you know, that follows from what I just said. Okay, questions? Factory interface. It has, now there can be different interface. There's no one common factory interface. Factory is a pattern, not an interface. Okay, so it's returning a certain type of object, and it's going to take a method that is consistent with the type. So you want a message filter. The factory name we are calling factory interfaces message filter creator. Okay, and I keep switching between message filter creator and message filter factory. And right now I have a GitHub conflict because two versions have different names, but hopefully this will get resolved and this will be the one that will be used. And you have get message filter here, and returns object to be created. Okay, and it takes no argument, and it can create a new object each time or return a singleton. Okay. A message forward creator now is a factory that implements this interface. And what does it do? it just says every time you want something, I'm going to create a new object. Anyway, all these objects are equivalent. Okay, just it's being lazy. It's not really storing that object in an instance variable, but it could. Okay. So is that a little bit more concrete? Okay. So this is an object. This exactly as Nick said, a class that has a method that instantiates another class. Okay. And what Nick suggested was this be a private method. Well, it's a private method. This class couldn't access that. But what you really meant was it was not a public method, and the factory could be in the same package. So it could be a protected method or just a default access. Okay. Somehow it's guarded. Okay. But in my examples, it'll be a public method to allow more flexibility, but perhaps less safety. Okay. I don't very much like this package-based access control because I keep refactoring packages all the time, and I say, oh, this shouldn't have been here, this is here, and it's not quite clear that there's a well-defined package for each class. You can have this collection of classes that are related. You have another collection that's also related. A class can only be in one package and not in multiple packages. So I've never quite liked that kind of protection. Okay? So that's part of the reason why I just make it public and say, and maybe it's less safe, but it's more flexible that way. Okay. So factory, understand at least that it's just creating. The object that wants an instance of a message forwarder does not instantiate it directly. It says get message filter from the factory. Somehow now it has to have a factory. So now what you can do is create your own factory that instantiates your own kind of filters. Okay?
But we have only one filter, right? In our assignment, one send filter.
Yeah. Yeah. So you can make a singleton. You have only one thing. We found a substitute. Try to do it without factories.
Substitute what?
I want to substitute a message forwarder with my own filter. How do I do it with just without a factory?
Like you add that class as the filter? I don't see why.
How would you do it? Just tell me concretely. Don't be abstract here. I gave you an alternative. I said communicator could have a get send filter, get receive filter. I told you why I don't want the communicator to go and know about all the other components. Okay? So how do I substitute? How do I make sure that the system uses your object and not my forwarder?
I don't know the exact syntax of the set message filter, what it does. So shouldn't it replace the...
No, forget the filter. You're telling me you don't want a factory, right?
Okay.
Fine. So give me a solution without a factory. Just forget what I do. Think from first principles. How do you make a system use your object rather than my object? I need some level of indirection.
Well, how does this setup
Okay.
finally change the filter? Is that what we're looking at right now?
Yeah, that's what you're looking at right now. Did you understand the factory I showed you earlier? Okay. This is my abstract factory. Okay? To this guy, I go and assign, it says, you can assign to it a factory. By default, the factory is this guy. Oh, sorry, I've got an angle bracket missing here. Okay? It's a message forwarder creator. And I can go and say, set message filter creator, my custom factory. Okay? So now we have static methods. Okay? And now we can't substitute this selector with another selector, but we assume there's only one selector. And I used to call it selector till somebody told me it's an abstract factory. Okay? So I'm just using the names I used to use. And an abstract factory allows you to switch between factories. That's what it does. So you guys will call set message filter creator, right? Who will call get message filter creator?
The communications class?
Somewhere in the code where where you're attaching filters. Somebody that knows about filters says, I need a filter. Okay? Because I know these are the two agents that have a filter in between, and I will go and call the get message filter creator. I will get the factory, from the factory will get the object, and I will put the object in between these two objects. Okay? And again, this is something I came up with. I didn't come up with all kinds of other alternatives, like the vector timestamp thing. I didn't go and think of your solution and somebody else's solution, and there might be a better solution than this. Okay, but that's why when I said think about it, I was serious about it. That there are solutions other than factories also, and it'll be nice because it's great when I see some concrete examples. Then you understand things better by comparing them with alternatives than by seeing them in an absolute way. I always say I learn things as diffs from what I already know rather than as absolute algorithms, right? Because there's only so many absolute algorithms you can know. Okay, so everybody understand how to change factories? This is a default factory. This is called during construction of send pipeline. Okay, and this is the send message filter selector. And it can be assigned custom send factory. You can say new my send filter creator before, and do this. Make sure you do this before the communicator is even instantiated, because when the communicator is instantiated, it instantiates other objects, which instantiate other objects. Somewhere in that process, which even I don't remember, a filter is attached. Okay, so make sure that the object is assigned right at the beginning. And this is something in a lot of tools. There's a configuration file that is provided. And in the configuration file, you go and mention classes. And the configuration file interpreter will go and take the class, instantiate the class, and create the factory. Okay? So you don't even have to go and use a selector. You can just have this configuration file.
In your communication library, you have already, do you have a default factory?
Yes, that is my forwarder factory, right? We saw that. Similarly here, this is my receive message filter selector, and it's also got the same factory.
Oh, okay, no. So we are just replacing the default factory with our own. Okay.
And that's all you do. And your get method is called whenever it needs to be called. But just make sure that before the library becomes active, you go and create this. I believe in the communicator, I've also put a set message filter and a get message filter. I might have put it, but I've given you reasons why that shouldn't be the case, and really wanted to teach you about factories also. But if you want to create pluggable components, this is the way to go. Okay, you might have heard of factory methods, which are different, and those are frowned upon, even though I use them a lot because it's better than not using factory methods. This you can see is a very long-winded way of doing things. Okay, and factory methods are much easier. Okay, if you don't know what factory methods are, again Google. Again, they will say deprecate it. It's not a good idea any longer. Okay, so there's a receive message filter selector and a send message filter selector. Okay, say nothing new here from the previous slide. Okay, so we're running out of time. You've got the whole architecture. Okay, you've got the algorithm. What you don't have is the traceable steps. Okay. Next time, I will explain to you the traceable steps, but there's nothing that prevents you from starting your implementation and putting the traceable steps later. The traceable steps just help make sure that you are on the right path, and also will allow me to at some point automatically create if it ever happens. But it certainly helps you debug your stuff also better. So there's a few more slides having to do with that. There are a few more slides having to do with what to do when concurrent messages are received. Okay, and you want to do something interesting with that. Again, you can postpone that till next Monday, or I'll write down enough information in my assignment for you to handle those. Okay, so we make this due next Wednesday, and feel free to use Piazza. And of course, I'll put these slides with the animations on in case you want to go forward. Okay, I thought I'll get more ahead, but. I often wonder whether algorithms are harder to come up with or software engineering patterns. And you guys came up with lots of algorithms, but it was a little harder for you to understand this level of indirection. And that's often the case. Somehow abstraction gets people more than algorithms. So it's good to teach that stuff. Okay. So let's review. I've given you the algorithm. Okay, I gave you the algorithm for the two-person case, and then I gave you the algorithm for the end-user case. And those of you who started it, you relate much more to what I'm going to say than the ones who haven't started. But you basically have to keep a local vector timestamp at each site, and you keep it so that you can process both send messages and receive messages. For send messages, before you send a message, you increment the timestamp and attach it with the message. Okay, and for receive messages, you keep an ordered buffer because when a message arrives, its causes may not have arrived, so you have to store it somewhere. So you keep a buffer there. And whenever a message comes in, you put it in the ordered buffer at the right place. You don't process, even if it's at the head of the queue, we're just going to say you put it in the buffer. And now you process as many messages in the buffer as possible based on the fact that this message has arrived. It may be only this message, or it might be messages that come after this message that are buffered, okay, that succeed this message. And if the message is empty or the message at the front of the queue is not the successor of your local timestamp, then you return. Otherwise, you keep removing messages that succeed your local timestamp till you have no such messages left. Okay, that's a basic algorithm. So semantics. Okay, and that apparently the application of it. And we said that look, we are going to keep the application unaware of causality, the communication system unaware of causality. So the causality is going to be done in filters. Okay, so it's like having in Unix a pipe where the last two endpoints don't do anything, and you put something in between that has awareness. Okay, and so the timestamping has to be done by the send filter. The timestamp checks have to be done by the receive filter. Receive filter also updates the timestamp based on what the received messages message that has been received. Okay, the sending guy updates the timestamp. The component of the timestamp that stands for the sender. Okay, and the receiver goes and updates other components of the timestamp. Okay, so they need to share data structures, and sometimes you need send filters without receive filters. Sometimes you need receive filters without send filters. So I have kept them separate, but in this case, you really need one filter, if you will. That's on the path, both paths. Okay, and you can do that by having both of them refer to the filter, the shared filter, which is the causality manager I'm talking about. Okay, when you look at operation transformation, same thing. There'll be another shared object. Okay, and this object is going to also get messages from the communication unaware system, and those are the client join things. Okay, because you're going to create a vector timestamp, you're going to create a component for each user. You have to know when a user joins. You have to know how many users joined. So that was the architecture. Okay, so send and receive filters, and the question was, how do you replace the causality filter with the OT filter, and how do you replace my current filter, which does nothing, with your filters? Okay, and we need some level of interaction, and I gave you three levels, and like I said before I started these slides, you could have had 2 levels also in this particular case because the filter is a singleton class. You only have one filter, one instance of it. Okay, so we said there are factories that return filters, and these are objects with interfaces, and they share common state, and common state can be passed as parameters to factory and filter constructors. Okay, so that's the part that's a little tedious, but that's a little bit of software engineering which you should know about. And the next question is, how do I test the system? Okay, so it's for causality issues to arise, I need in your system. So supposing you're doing your assignment 2 again now. Okay, that's what I've asked you to do. What constraints do you have to put in assignment 2 to show that causality works? When you do your demo, you have to somehow delay messages. Okay, and then another constraint you have to put. So the communication can be between 2 processes happens directly or indirectly. I left that up to you in assignment 2. You could do it relayed or you could do it P2P. And in this case, you have to do what?
Direct.
P2P. Otherwise, we wouldn't have any problems. Okay, so we know how to go and change from P2P to relayed. I've told you the API. Okay, how to ensure the messages from PC1 take longer to reach PC2 than PC3. And I could have asked you guys to do it, have some more fun with threads. Okay, but a lot of you in your assignment one did do threads, so you've got that practice. And I've just made things very easy for you. You just tell the communicator that on a particular site, that messages from me to this particular site should be delayed by at least this much. Okay, why do I say at least?
They can always be more.
They can always be more. We know that we get delays when we use systems, and none of them are intending to give you delays. Okay, but they just happen. Okay, and they happen because of processing speed. Okay, so some guys gotten behind. Maybe the processing speed of the routers, which means the network delays. Okay, and the fact that there are multiple things running on a computer, so threading issues. So nodes labeled in terms of their users. Okay, so we don't have to go inside this particular host. We just say Kathy's host. Okay, and actual delay may be larger because of scheduling and network delays. Yeah.
That's milliseconds, right?
Yeah.
Okay.
And I was doing my demo, and I had to go and make sure things are causal. So I think I put 20 seconds there. Okay. Okay. So I hinted that there's threads there. Okay, because when a message gets delayed, you don't want the sender of the message to get delayed, right? The sender should just go on, and it's as if the the delay occurred somewhere else in the router. Okay, that's what you're really modeling. So you're modeling on a single computer two asynchronous pieces. Okay, and in general, you guys you haven't got full control of the communication pipeline, and there may be multiple stages there, all running asynchronously. Okay, so you have a timestamper. We want that to go and run asynchronously from the delayer. Well, at least we want the message producer to run asynchronously. Your timestamper is a filter. You don't know in what thread the filter executes. Maybe it executes in the same thread as the timestamper, as the message producer. Okay, and to be honest, I've forgotten in which thread the filter really executes. Okay, but we know the filter executes somewhere in the pipeline. Okay, so and so if the timestamper executes in the thread of the message producer, then the timestamper and the delayer should run in separate threads. Okay, because we don't want the message producer to be slowed down. Okay, and maybe the broadcaster goes and runs in yet another thread. Okay, can you guys see your life being complicated by this fact? I mean, do you have to be aware of synchronous versus asynchronous transmission? When we talked of synchronous and asynchronous, we said synchronous is always easier on the programmer. Somehow, synchrony makes a difference to the programmer. And if you're saying, no, it doesn't have to worry, then you're having your cake and eating it too. If you can't send the next message till the first message has left your computer, there are certain guarantees you can assume that are not available if you're sending messages asynchronously. And can you see some guarantee that you don't get with asynchronous communication that might complicate your algorithm? Okay. So if there are asynchronous pieces, that means there's a pipeline, right? Just as on a computer architecture, you have pipelines. That means the message you are currently timestamping may be ahead of the message that the delayer is looking at, which may be ahead of the message that the broadcaster is sending. Can you see now a problem? Okay. So let's say you wrote this code in the timestamper. A new message comes in, you increment the timestamp, you set the message timestamp to the local timestamp, and you go and tell the message processor to process the message, which is the next stage in the pipeline, which then eventually gives it to the delayer. How many of you have written haven't gotten to this stage of have written this code, this part of the code? Nobody? Good. Has anybody written this code? No.
I was trying to write it.
You were trying to write it. Did anything go wrong?
So the set message in the group message interface, it has the get timestamp the function, but it's return long. I need to change it to like my own timestamp.
So there's some conversion you're talking about.
Yes.
So that it's got long and you want to keep an int?
I want to keep a
Double?
object. It's my own defined object.
Okay.
Like the timestamp.
Okay. So let's just get this one part clear. The timestamp in the group message is the real timestamp. Please don't try to mess with that. That's just the message, the real time. You have to keep a vector timestamp, which is totally orthogonal to that timestamp. So don't try to convert one to the other. Okay. So this is this is set timestamp. I really should say set vector timestamp. Okay. So I did this code, and I had to spend many hours of debugging to figure out what went wrong, because there's a pipeline. Yeah.
Do all three of those have a reference to the same vector?
Well, if I do this code in Java, what's going to happen? I set timestamp to my timestamp. It's going to get a reference to my local timestamp. And now, when I increment it next time, I increment this guy's timestamp also. Okay?
You could make a new thing.
So you have to do a new timestamp. You have to do, what's a technical term for it? So you have to create a deep copy, not just a shallow copy, a deep copy. Okay? So incrementing timestamp may change timestamps of previous unsent messages. Okay? And this is a very, I teach deep and shallow copy in classes, and I made this mistake. Okay? And I tell people about, hey, the problems of asynchronous communication and how buffers, you have to worry about the buffering issues. And, there you go. Okay? So I could let you guys learn it the hard way, or I could tell you that please create a deep copy. Okay? So is there a deep copy method in Java in an object? There's a clone. What does clone do?
I don't know.
So I actually teach this stuff in 401, and you should go look one of my slides exactly what clone does. But clone is a protected method. It's not really a public method, but you can make it public. You can always, in a subclass, increase the visibility. You can't hide. You can reduce. And that does a shallow copy. Okay? It depends on what's been inherited from the superclass. Okay? And so is there no deep copy in Java that I could use automatically?
This is your written class, so you have to.
So right now, this is my timestamp.deepcopy, right? It's your class. I'm not giving you a timestamp. You guys have to implement your own timestamps, by the way. I want to make it very clear.
The timestamp, the vector timestamp is our class. Right?
Yes, it's your class.
We'll have to write it.
You'll have to write it, but I'm very nice. I give you a method to do this. And how is my method working? If Java doesn't provide me with this facility, how am I doing it?
Serializes it, unserializes it.
So Java gives you serializability automatically. Can't you just exploit that fact to give a deep copy automatically? Okay, that's what I do. Okay, I use Java's ability to serialize objects to go and create a deep copy. Okay, and you'll get an exception if your object is not serializable. Okay, but it needs to be serializable for it to be able to go across a network. So please use this. Okay, I'm glad you guys didn't get to this stage and spend many hours debugging. Okay, but you would find the problem, and that's the fun with concurrent programming. Okay. Questions? Okay. So it returns, what I do is, if the object is not serializable, you get back the original object. Okay, so then you run into the same problem.
So does it throw an exception?
No, I think I claim that I'm returning original object. Okay. The reason why I do it this way is that I use this stuff in a tool that I built for COM 401 students, and many of their programs will run just fine if the copy is not made, and they don't know serializable things. So if they happen to know serializable interface, then I do a little better job for them, and it becomes more efficient, I think, if that happens. So that's why I did it. I did it this way. Okay. But just you run into other problems in your assignment if it's not serializable, because ultimately it has to go over the network. So eventually you will get a problem. In one of the softwares that I had, in some exception handler, I just did nothing. I didn't even print line. I did nothing, and that caused my students a lot of trouble. So I've been worse than this. Okay, but when you write code, you forget to do it, print certain things sometimes. Okay, so yeah, you won't get any exception if the object is not serializable. Okay, questions? Okay, so we've got the whole architecture. Now we know also that we have to do a deep copy. We've got all these components. So let's very quickly go through the algorithm. Okay, and especially when I'm surprised you're the one who started first. You're the one who always starts at the end. So if you don't do that well, I don't get bothered. I said, oh, he starts in the end. Okay, but if Chu doesn't do well, I know he starts early. So that will bother me. Okay, so let's go and see the algorithm for each of these components. Initialization. Okay, so initialization, you've got to create a causality manager and pass it to both the factory of the send filter and the factory of the receive filter, so that both of these filters get these objects. Okay, and the causality manager, when it comes up, does it have to do something? Initialization, what does it have to do? The reason you have a shared causality manager is because you have a shared data structure, and the shared data structure is what? The timestamp. So when it initializes, it must create the initial timestamp. Okay, so don't forget to do that. Obviously, you won't, because the other steps won't work. And what is this arrow? You guys remember this? I just talked about. So whenever a client join happens, what do?
You increment the vector size.
If you have a vector, you increment the size. If you have a table, which is what I would recommend actually, you add an element to the table. Okay, the table is going to be less efficient, but it's easier to deal with. Okay, and now when a message comes in to the send filter, what do? Sorry, when a message is produced, what do you do? So send filter's got the message now. Yeah, right. So your application just sent the message. The send filter got it, and the send filter is going to do what when it receives the message?
Wrap the message with a timestamp and send it to the processor.
Send to the next stage. Send to the communicator. Wrap the timestamp with the message. See, the advantage of doing the assignment, he's the only one who's got it all right, more or less. You wrap the timestamp. You wrap the timestamp with the message, and will all messages have the same timestamp? You first increment, and then send the message. Okay. And the receive filter, when it receives a message, okay. You have to process the timestamp. You compare the timestamp with the local timestamp, right? But will every message, the send filter, will every message be timestamped by the send filter? Non-user messages will not be timestamped. Okay, so receive filter must similarly look at whether it's a user message or a not user message, and then do the processing based on the timestamp, right? And either the message will be buffered and then after that processed. Okay, and then of course it has to deliver. Okay? So you've got. And when you wrap the message, before you wrap the message, create a deep copy of the timestamp and then wrap the message. Okay, just remember to do that. Okay, so let's go and see the steps now. Initialization. So this is traceable algorithm. Okay, so I already gave you the algorithm before. Now it's algorithm in terms of the components somewhat, but more importantly in terms of the traceable steps. Okay, so initialization, vector timestamp created, okay? And you pass the initial timestamp to the trace so that if I'm grading you, I can check whether you have initialized it correctly. Okay, and I assume a certain format in this for the timestamp. That format is a table. Okay, and so make sure that when you send the table, if you're just going to send your table to me, make sure again you create a deep copy of it before you send it to me. Not that I'm going to do anything with you in the tracer, but it's just safer thing to do. Okay? Because if I'm storing it and you keep changing the timestamp on me, then by the time I go and grade your stuff, I might have the wrong timestamp in that tracer. Okay. Join message for each new user you add user added to vector timestamp. Okay, so tell me that a new user has been added and give me the new timestamp. Okay. Send steps. Send filter for each sent user message as opposed to system message. Okay. A long name here to tell you exactly what's happening, that the local count is incremented in timestamp. Okay. So if you program with INJ and you look at this and say, oh my God, I'm going to spend all my time typing, and especially if you're not a touch typist like I am not, this is a problem. But in Eclipse, is that really a problem? You can just ask it to complete it. Okay? In fact, even if when you're declaring a variable name, it'll suggest some names to you based on the type of the name. So I often use even that feature. Okay? I had some names that were really long. I've actually shortened the names somewhat. If you're not going to comment your code, you might as well write paragraphs when you're naming your method variables. And then vector timestamp sent through message processor. Okay? So then you go and announce the step that you sent this message. And if it's a non-user message, just pass unfiltered message to message processor. No tracing steps have to be triggered. The regular tracing steps in communication are triggered. Receive traceable steps, receive filter. So for each vector timestamped message received, okay, so throw a little event when you receive a message that is vector timestamp to say tell me that what message you received, okay. And for each of these messages, now what do you do if it's concurrent? Stop, throw an exception. I allow you to do that, I think, right, in the assignment specification. But you might want to do extra credit. So I'm just saying do something, okay? I'm not going to get into it at this point. We'll a little later see what some alternatives are. In fact, after this, that's going to be the main issue we're going to discuss in the next set of slides, okay? With the local. Okay, so that's a global variable. The local timestamp is the local variable, so this is concurrent with that. Okay, so you must have this check. If you don't have this check, then you didn't need a vector timestamp. You could have just used a scalar number, like the kind of algorithm that was suggested. We do that. We just have a number, and each time a message arrives, we increment the number. Okay? So at least I know that you have a vector timestamp if you throw an exception. Okay, but hopefully, if there's no concurrent, then we go and buffer the message, okay, and now we start processing the buffer. So if the head of the message is successor, then we go and remove the message from buffer, and then we give it to the message processor. Okay, so two different events occur, and I want you to fire events for both of them. Okay, that you removed it from the buffer and you delivered it. Okay, and somewhere here in the buffered, I ask you to tell me where you put in the buffer. Okay? You may put it wrong. So not only do you pass the vector timestamp, but you also pass the index of the position in the buffer where you've inserted the message. Okay? So that you do it correctly, because you can have mistakes there too. Okay, and you keep doing these steps until there are no such messages. Okay? Okay, so this is just the same algorithm before in terms of the traceable steps. And receive filter for each non-user message M, just do what you would do. Okay? Questions? Is the light all right? Do I have to dim it even more? I see you staring at it. Lights. I had it on medium. Should I do it night light? Now I can't see you guys staring, but you won't stare. I can still see. Okay. Okay. So let's talk about handling concurrent messages. Let's go and see whether we can do something better than just throwing an exception saying that shouldn't have happened. Okay. So why not just assume that the concurrent message commutes with let's assume that the concurrent messages all commute with each other. Okay. So you might want to immediately deliver the message. So when a message arrives, see if its vector timestamp is greater than one of the timestamps. I modified the slide in the next slide to get this. If its vector timestamp is greater than the timestamp, and put it in the buffer and process buffer. Okay, just check if it's that's what we do normally, right? And otherwise, deliver immediately, optimistic. What's wrong with this? I'm just assuming that that message was concurrent with my previous message. One person went and changed the color of a line, the other person changed the size, they commute. So if the message is greater than my timestamp, okay, then it's a causal message. I mean, it's causes I will receive eventually. Okay, or maybe it is the next message. If it's concurrent, just deliver it. If I buffer it, that message never gets processed. I could do that too. I could just go and discard it. I could do many things here. I could discard it, but why not just process it? Because assume it's commuting.
By processing, do you mean increasing the timestamp and all?
Oh, I don't know. Right now I'm just saying give it to the next stage. Deliver it to the application. So should I change my local timestamp? No. What would go wrong if I change my local timestamp? Because this message will tell me, that this message has arrived from a particular site. Shouldn't I go and change the count for that site? And the counts for any, so if I do that, what may go wrong?
Is it possible that if we have concurrent messages, and we update our vector timestamp, then we could like not receive one of the concurrent messages and continue processing messages that should be depending on that message?
Okay, so the danger is that's exactly the problem, that there was some thread that you were processing so far, that your buffer reflected, right? And you're expecting messages to be increasing in that thread. And you're seeing whether the timestamp is greater than the local timestamp. And now, if this message comes in, and did you say that, and you said the problem arises if we change our timestamp, right?
Yes.
If we change our timestamp, now the messages in that previous thread are no longer greater than my local timestamp. Right? So I'm in trouble. But what about messages in this new thread? Now, in this new thread also there may be some successive messages, right? So those I will be able to process. But if I don't change the vector timestamp, what bad thing can happen then?
then we won't ever process those messages.
Then we won't process the messages. We will never look at the causality in the next in the other thread. Right? So we have at least 2 threads at this point, and I will go and I can either honor causality only in one thread, in which case I never update the vector timestamp. Okay? Or I want to go and do it in the latest thread, in which case, I have a problem. Okay? So if you update timestamp, subsequent causal messages with respect to previous messages or messages in the previous thread will not be processed. If I do not update timestamp, subsequent causal messages with respect to this message not processed in order. They are processed, but not processed in causal order. Okay? And I should really, okay, I have to change this thing a little bit. So is there a solution to this? And by the way, again, please, I've suggested something to you in the assignment. I've given you an algorithm, which I'm going to talk about, not algorithm, but an outline of an algorithm. And please feel free to check on the web for this situation, for this case. Like I said, this literature is very, very big, and to find, and it makes a little, the assumptions it makes are a little different from what we've made, and the application is very different from our application, is fault tolerance. So hard to actually find the algorithm to handle this situation, and it's maybe easier to come up with our own algorithm. But if we do that, there is no guarantee about the proof, because proofs of these algorithms take forever and are very, are very deep. So feel free when you're doing your assignment to find an algorithm with a proof, or just find an algorithm. But if, assuming we can't find, can you suggest some changes to our algorithm to handle both threads?
Could we merge the timestamps in a way that adequately reflects our knowledge of each other sender?
So if you could somehow merge the timestamps, that may solve the problem. But when I went and updated the timestamp, I indeed did merge, right?
Okay.
In fact, merge is what you don't want to do. That is a problem, at least the way I see it. So if you're not merging, what are you doing?
Replacing.
Replacing, okay. Replacing or?
Could we branch, and we now have 2 different queues of messages?
What about that? We branch and have 2 different queues of messages, have 2 different vectors timestamps, each associated with its own queue or buffer for the 2 threads. And then whenever a new message comes in, you go and say, am I greater than this thread? Am I greater than this thread? Or create yet another thread. You can code it. I don't know if it works right or not, but it seems to work right in my head. Okay. So how in general, there's a tree, right? You started with nothing. You branch at some point, which can further branch and keep branching. Right? So how many, given a tree of concurrency, how many vector timestamps will you have? Sorry? No, what is n?
The number of that is sending the message.
So n is the number of nodes or the depth of number of? Number of leaf nodes. Okay. This is a vindication that this may be right. Okay. Somebody else is also thinking along this. Okay. A tree of message paths exists. Okay. This is the way I'm reasoning it out. Create vector timestamp and buffer for each leaf in the path. Okay. Which basically means that every time you see a concurrent message with respect to your current vector time, just create a new one. Okay. And I copied this text onto the previous slide, so I was hinting multiple timestamps in the previous slide. I'll go and change that to the unique vector timestamp there. So when a message arrives, see if it's vector timestamp greater than one of the vector timestamps and put it in the buffer for that vector timestamp. Okay. Otherwise, create a new vector timestamp buffer. Okay. So if you're going to do this algorithm as extra credit, then you should fire this particular. I think I shortened the name. I think I did. I think I removed the in response to concurrent message. That was a little too much because that's implied. So, that's what you do. Because okay. So, and see if it works. I'm very curious. I didn't implement this algorithm. Okay, so this is extra credit and worth a lot of points if you do it. And I tell you guys to go and take the examples we saw in causality earlier and run them through this to see whether at least that stuff works. Okay? And going from 1 to n is not hard, right? It's just a question of some elegant programming. So it shouldn't be too hard to be checking a whole list rather than checking a particular timestamp. Okay? Questions? Okay, so let me summarize what we've done here. We've assumed reliable delivery, and we've looked at in order. Okay, we looked at 2 sites first, then we looked at n sites, and we saw that we want to send a logical timestamp with each message. That timestamp, logical time, might be a scalar, as was suggested, one of the solutions, or it might be a whole vector, which allows you to figure out concurrent actions. And then we have this algorithm. And the whole idea is that when you're sending logical timestamps, you'll buffer things for later playing. Okay? And it's very interesting, if you look at Wikipedia and look at the first thing that comes up in Wikipedia on this thing, they never talk about buffering. And they talk about just whenever a message comes in, merge the timestamp with your timestamp. So I'm not quite sure whoever wrote the Wikipedia article what application they were considering. But like I said, these papers are very long, involve fault tolerance, and the Wikipedia article doesn't mention fault tolerance there. So buffering in our little world at least is important. And in multi-party messages, you're sending a vector timestamp. And that's the semantics. And then we were talking of the engineering of it. And we want to allow easy switching of this scheme. Given that there is this plethora of algorithms around, we want to change them easily also. Okay. And in our again, this should not be OT manager. This should be causality manager. Okay. I copied the text from somewhere else. I actually saw it this morning and forgot to change it. And we are using abstract factories to instantiate filters. Okay. And I personally, the algorithm that I've developed is based on a talk I heard 20 years ago from a guy called Ken Berman. And he was talking of vector timestamp in a system called ISIS. It was a toolkit. And he was using for banks and reliable computing. And anybody heard of Ken Berman? Anybody heard of Mike Reiter? So Ken Berman came here. I listened to his talk 20 years ago at Purdue, and then he came here later. I said, "Oh, Ken, I didn't know you were that Mike was your student." And he said, "No, I'm his advisor." And he's very modest. Ken Berman is very famous. Okay, so he's a really nice guy. So anyway, so like I said, from that talk I heard about vector timestamps, and based on that I've developed this algorithm. And just because, like I said, there's a whole forest of algorithms around with different conditions. And once you get the idea of vector timestamp, you can see that the algorithm, seems to work. Okay, and I'll say seems because we haven't got a proof of correctness. Okay, proofs of correctness. How many of you have taken Jim Anderson's courses? You have? And how big is the algorithm and how big is the proof? Right? So the whole idea in his course is that you prove algorithms right, and I give you an algorithm and I tell you to implement it. That's the difference.
More interesting.
Sorry?
More interesting to implement.
More interesting to implement. But if you have a proof, then everybody in the world is going to refer to your proof. Whereas your implementation, I see in the video and I say, very good, and you get 140 points, and that's it. Okay, that is for posterity. Okay, till somebody finds a bug with your proof. Okay, and of course, having been in the program committees of various conferences, when a proof comes to me and I just try to find all the theoretical people who can check the proof, and they hate proofs. Because who wants to go and study a proof, right? Intuition is great. You look at the intuition, it seems fine. In 20 minutes we figure out it's right, and we say, yes, it probably works. Until some user cries that, it doesn't work, we are happy. And proofs, they don't like to go and check each other's algorithms either. So when I see something with a proof in a conference paper, especially journals a little different, but even in journals that happens, I'm very suspicious. Okay, so